So the first thing you want to look for when you're determining convergence is you want to look for a series where n goes to infinity, the limit does not equal 0. So that would be the first one. So this guy here is going to diverge by the nth term test. And I can tell that because if I take the limit as n approaches infinity of this expression, I get 16/3, which does not equal 0. So this guy is going to diverge by the nth term test. Let's take a look at this next one. So if you were able last Thursday and Friday to learn the alternating series test and do the homework on it, this is going to be an alternating series because if you plug in an odd value for n, you're going to get the term is going to be negative. And if you plug in an even number for n, you're going to get a positive term. So the signs on the terms in the series are going to alternate. So this is an alternating series. And you'll learn if you go back and watch the video over alternating series. There's actually two, one that I did and then a video that the College Board did. There's 3 conditions that have to be met. It needs to be alternating, which we already talked about. This one is alternating. The limit as n approaches infinity of this term has to equal 0, and it does. And then one more thing is if we plug in an n plus 1, for n, that has to be smaller than the original expression. And it is. Every time n is a positive integer, this expression is going to be less than 1 over n to the 5th. So this one converges by the alternating series test. And if you didn't learn that last week, of course, that's not going to make much sense. So go back and learn it, and that'll make more sense. Okay, so number 3, I'm going to erase this in a second. So if you want to screenshot that, you can. Number 3, this guy, if you see the n's as powers, it's probably geometric. So what I noticed when I was grading a lot of the integral test homework is that people were having trouble recognizing the geometric. It happens when n is in the exponent. So this is a situation where we can separate that denominator into 8 to the n and 8 squared. So this is going to be the same as 6/8 to the n power and then 1 over 64. Why 1 over 64? Because that's 8 squared. So our series we could rewrite this way, and this would be a geometric series. And this one would converge. Okay, one other mistake that I was seeing when y'all were finding the sum of a geometric series, you have to pay attention to what the starting value for n is. So n equals 1 is the starting value, so you plug in 1 here for n. So the first term in this series is 6/8 times 1 over 64. So if you're finding the sum, this would be the expression that would go in the numerator when you find the sum of this series. And we know that the series does sum to a finite value since the absolute value of r is less than 1. Okay, so you'd use geometric on number 3. Number 4 is an alternating series, but the alternating series test only works for a converging series. It's only a test for convergence. If we were to find the limit as n approaches infinity of this expression, it would not equal 0. Because if you look at this part, the n plus 1 over the n plus 3, the limit of that as n approaches infinity would equal 1. I don't care if the signs alternate, the limit or the terms are going to alternate between close to 1 and close to -1, close to 1, close to -1. Those terms are not going to get closer and closer to 0. So this guy is going to diverge by the nth term test. The limit doesn't actually exist. The limit's going to, like I said, the values are going to approximate 1 and -1 and oscillate as we go toward infinity, but it does not for sure approach a limit of 0. The terms do not get closer to 0, so that diverges by the nth term test. And then lastly, this guy is p-series. You could use the integral test on p-series. You don't have to. So this is going to be, you can bring that 17 to the front, and then this is 1 over n to the 1/2. And p in this problem is 1/2. P is less than or equal to 1, so that tells us it diverges by p-series. Okay, so it's just like a real quick overview of the convergence tests that we've learned so far, because we're going to start talking about one new one today, and I just wanted you guys to kind of be comfortable with those before we move on. This is the last convergence test. The one we're learning today is the last one that you're going to see on the AP test. So the integral test is not on the AP test. Neither is the nth term test. All that ones are very easy one, but the other 3 that are listed here are going to be covered on this year's AP test. We have to get really good at working with factorials. This is one of my favorite things to teach. I love the ratio test. It's super fun. If you're good at algebra, you're going to love this. So let's go ahead and dive in. So as you know, 5 factorial is equal to 5 times 4 times 3 times 2 times 1. 6 factorial is 6 times 5 times 4, etc. Okay, so if I had the expression 5 factorial over 6 factorial, and I'm going to switch to a darker color. That one's not showing up very well. If I have the expression 5 factorial over 6 factorial, let's take a look here. So I've written out what 5 factorial is equal to. Do you see how there's another 5 factorial right here? So 6 factorial is actually equal to 6 times 5 factorial, because this underlined part here is equal to 5 factorial. So that makes it really helpful down here. I can go ahead and substitute. In place of 6 factorial, I can substitute 6 times 5 factorial. So then we can just cancel out those 5 factorials, and 5 factorial divided by 6 factorial is 1/6. Cool. Super fun. Okay, so next, let's simplify what's on the bottom there. We have n plus 2 factorial over n factorial. Well, just like on the previous page, when we wrote out, and you don't have to write this, when we wrote out 6 factorial, we counted down from 6. 6 times 5 times 4 times 3 times 2 times 1. So we're going to do the same thing with n plus 2 factorial. If you imagine that n plus 2 is an integer, I'm counting down from n plus 2. If I go to the next consecutive integer going down from n plus 2, the next consecutive integer would be n plus 1. Let's go down one more time. We would get n factorial, or I'm sorry, n. Let's go down one more integer. So I'm counting down from n plus 2. So I'm going to have n plus 1, n minus 1, and then n minus 2. And then I'm going to keep going. So I'm just going to put a factorial there because that shows me I'm going to keep going and counting down from there. So if we were to do the same thing for n factorial, that's going to equal n times, let's multiply by the integer that's 1 less than n, which would be n minus 1, times the integer that's 1 less than that, so that would be n minus 2, and so on. So look at what we have here. Again, these underlined expressions are the same. So in place of this squiggled underline expression up here, I can just replace it with n factorial. So that helps me down here simplify this. So this is the same as n plus 2 times n plus 1 times n factorial over n factorial. And then the n factorials just cancel. Super fun. Okay, I'm going to give you one to try. So see if you can simplify that expression in the denominator. Or simplify the expression at the bottom of the page. Okay, so n factorial is the same as n times n minus 1 factorial. And then we still the n minus 1 factorial in the numerator. Those n minus 1 factorials would cancel, and we would just be left with 1 over n. We're going to use the ratio test when we have a mixture of different functions. You might see a polynomial in your series, like n plus 1. You might see a factorial in your series. It might be alternating. You might see an exponential. So if you have a mixture of a bunch of different things, you're going to use the ratio test. If you just had an expression like 10 to the n over 5 to the n, that would just be geometric. It's when you have a mixture of different kinds of expressions that you're going to use the ratio test. So we are going to find the limit as n approaches infinity of the absolute value of a n plus 1 over a sub n. So this guy currently is a sub n. Let's rewrite this problem by finding a of n plus 1. And by the way, you guys are familiar with how to divide fractions. This is going to be equal to a with a subscript n plus 1 times the reciprocal of a sub n. So that's how we're going to attempt this problem. We're going to take the expression a with a subscript n plus 1 and multiply by the reciprocal of a sub n. So how do we find a with a subscript n plus 1? We're going to go everywhere there's an n and replace it with an n plus 1. So that's going to be 10 to the n plus 1 over n plus 1 factorial. Okay, so we just took care of this part of our limit. So in the upper right hand corner, I put a check mark here because we took care of that. Now we're going to multiply it by the reciprocal of the a sub n term, which is just the reciprocal of what we were given in the original problem. So the reciprocal of this guy goes here. Okay, now is where it gets fun. We're just going to do some algebra and rewrite this. So we have the limit as n approaches infinity, absolute value 10 to the n times 10 times n factorial, and I'm just making it one single expression. Now remember, on the previous couple of screens, we talked about these factorials. So now I'm here to this n plus 1 factorial. That's the bigger of the factorials. So I'm going to start counting down. N plus 1 factorial is going to equal n plus 1 times n factorial. You count down until you get to the smaller expression. So I'm just going to take this expression I just wrote on the left and replace the n plus 1 factorial with that. And then we have 10 to the n. This is so satisfying because you take this really complicated looking expression and we're going to cancel some stuff out now. So the 10 to the n power cancels, the n factorial cancels, and we're just left with 10 over n plus 1. So that's an easy limit to find as n goes to infinity. I don't need to worry about the absolute value. Since I'm plugging in positive numbers, this guy is always going to be positive. And since the denominator is going to get much, much bigger than the numerator, that limit's going to equal 0. So let's go back to the previous screen. If the limit was less than 1, the series converges. And we got our limit to equal 0, which is less than 1. Therefore, it converges by the ratio test. I love the ratio test because it's the same process every time. How do we know when to use it? When we have a mixture of different kind of expressions, factorials, exponentials, polynomials. Okay, let's try another one. I'm going to actually save this one for you guys to try on your own if you wish. This is a pretty challenging one, and here's a super big hint I'm going to give you. That guy equals E. If you took pre-cal, you might have done compounding interest, and you might have derived E by finding out what happens to an investment if we don't compound interest like daily or even hourly or even by the minute, but if we compound interest continuously. And what happens is if you compound the interest continuously, the value of the investment is going to approach E if you invest $1 and it's compounded continuously. So that's where E comes from, and that it's equal to this. So go ahead and try this problem later, and this is a big old hint. But we can do this guy. So let's go ahead and rewrite him first by moving the E to the n to the denominator. So again, why are we using the ratio test here? Because I just see a mixture. I see an exponential expression in the denominator, and I see a polynomial expression in the numerator. So we're going to rewrite this. A subscript n plus 1 times 1 over A subscript n. And after we do this example, I'll pause in the recording and see if there's any questions. Okay, so we're going to take the limit as n approaches infinity of, so I'm going to go everywhere there's an n over here in this expression on the left, I'm going to replace it with an n plus 1. So I'm going back here and replacing those n's with n plus 1. Okay, so now I'm going to multiply by the reciprocal of the expression that we're starting with. So I'm going to flip this expression and put its reciprocal in the absolute value. So e to the n over n squared plus 4. Okay, sadly, there's no factorials to rewrite because those are fun, but we can rewrite the exponential expressions. Hey, I'm so glad you guys like joined in with me today. Like this is just like fun learning this stuff. So it's fun to do ratio tests by myself, but it's even more fun with y'all. So I'm glad you're here with me. So I'm going to rewrite this denominator as e to the n times e to the 1. And then I have times e to the n here, and then n squared plus 4. So not very much cancels here. Just the e to the n's are going to cancel. So caution, you cannot cancel the n squared out. Since this n squared, the n on top is, oops. Since this on top is added to the 4, the n squared can't cancel. So what do we have? We have the limit as n approaches infinity, n plus 1 squared plus 4 over e times n squared plus 4. Okay, so now when we take that limit to infinity, let's look at the degree. The degree of the numerator is 2. The degree of the denominator is also 2. So if we look at the ratio of the leading coefficients, the ratio of the leading coefficients is going to be 1 over e. That is surely less than 1. And so again, we have convergence by the ratio test. This is the last convergence test that you need to know that's on the AP test. So let me pause the recording.